Hi everyone, welcome to this lecture number 3 of week 7 on the course on non-linear systems. My name is Ramkrishna Pasumarthy. I am a faculty member at Electrical Engineering IIT Madras. So in this lecture we will derive certain conditions which will guarantee existence or conditions which will establish whether or not there exists certain kind of bifurcation points. So far we have looked about what is bifurcation and what happens qualitatively, what is the qualitative change in the in the system we see as the system experiences a bifurcation or there is a bifurcation point, right. So, let us revisit and do some observations of all the bifurcation diagrams before we derive certain necessary and sufficient conditions, right. Okay. So, let us start with the saddle node bifurcation. Okay. So, and I will use mostly the bifurcation diagrams to arrive at conditions. Okay. So, first if I look at this picture I can make two observations. The first observation is a unique curve of fixed points or equilibrium points, right, pass through the origin. And not only that, this curve was entirely on one side of mu equal to 0, right. So, it just on this side of mu equal to 0, right. So, there is nothing on when mu is less than 0. Okay. So, this is one observation here. A general observation which we had last time was these conditions. So, f00 is 0, df by dx at 00 equal to 0. What we saw is that these were necessary conditions, but not sufficient for any bifurcation, whereas we had one example x dot is negative of x cube or some mu minus x cube. We will again revisit that example. So, these are necessary, but not sufficient. So, we will derive conditions which what we need in addition to this to observe or conclude any kind of bifurcation in the system. Okay. So, this was in example 1. In the example 2 or in the second case we had two curves of fixed points okay, and then which intersected at the origin. The two curves are x equal to 0 and x equal to mu, this one and this one. Okay. Now, contrast to the previous case, both the curves existed in either side of mu equal to 0. Here the curves did not exist to the left of mu equal to 0, here you have on both sides. Okay. Only thing is that the stability properties of these curves changed as they passed mu equal to 0. Okay. Now, the third one, in this case. So, what we see is that in this example, two curves of fixed points intersect this plane. Only one curve existed on both. So, you have two curves, right. One curve was x equal to 0, second was this one, x square equal to mu. Okay. So, the distinction here was that only one curve, and this for both the subcritical and supercritical Pitchfork bifurcation. Only one curve, namely x equal to 0, existed on both sides of mu equal to 0, and the other curve, this one, lay only on one side. And this has a stability property which is opposite to x equal to 0. Okay. Now, these are the main observations, and here in this example what we saw was, even though this condition is satisfied, f(x) f(0,0) is 0, df by dx at 0,0 is equal to 0. What we saw is that this had a unique curve of fixed points. Okay, if I were to draw it, okay, let me just spend some time drawing this. Okay. How does mu equal to x cube look like? It's something like this. Okay. And the vector fields are such that, okay, everywhere they are just doing this. So, for mu, here I am looking at positive values of mu, and here negative values of mu. The stability properties do not change, even though you had a 0 eigenvalue, right. So, the stability properties do not change with as mu changes from changes sign from mu less than 0 to mu greater than 0 via mu equal to 0. So, these conditions do not say much, they do not really help me in deriving whether or not there exists bifurcations. What kind of bifurcation is still a different question to ask. So, what we will do now is just spend some time to derive these conditions for bifurcation points, and we will make use of the implicit function theorem. Okay, so let us start with the first one. So, I will do the first one in detail, and then the next one I will just mention results so that you could work out the steps by yourself. The saddle node bifurcation. Okay. Again, so we will just read these two statements again. A unique curve of fixed point passed through the origin, and this curve was entirely on one side of mu equal to 0. In this case, it was on the right of mu equal to 0. So, first is, if I look at the first statement, when a unique curve of fixed points passed through mu comma x is 0 comma 0. Okay, and this curve was such that this curve was tangent to mu equal to 0 at x equal to 0. this one. So, this curve, when I say this curve was tangent to this one, I am essentially talking of this one. This is a tangent, right? So, mathematically I can write this in the following way, that this means that some d mu by dx equal to at 0 was equal to 0. Okay. And the second condition, which said that the curve laid entirely on one side of mu equal to 0. So, the condition 2, the same color, this would mean that d2 mu by dx square is actually not equal to 0. I am so far not writing strictly greater than or less than 0, and I will tell you shortly why. Okay, so let us say now I am looking at a general scenario. General scenario of x dot is f x comma mu, again one day bifurcation. Okay, so with a fixed point x comma mu equal to 0 0, this is my equilibrium. And additionally I can also say this one, df by dx. So, suppose this also holds true, equal to 0, and third, okay. So, what do these conditions mean? Okay. These two conditions first, so whenever I want to evaluate this quantity, it should first mean that I should be able to write mu as a function of x. Only then I can differentiate, right. So, this mu should actually be a function of x, and then I should be able to evaluate its value at x equal to 0, and this should go to 0, which means, so now I have a function of the form f mu comma x equal to 0, where I should be able to write mu as a function of 0. I go here to the implicit function theorem, sorry, where I had a function f x comma y equal to 0, and I wanted to write y as a function of x such that f x comma g of x equal to 0, and this was possible only when df by dy was not equal to 0. Therefore, equivalently I can write this condition now as df by d mu at 0 comma 0 is not equal to 0. This actually means now that I can actually write mu as a function of x. Okay. So, if this holds, okay, this is the third condition, right, which seems obvious, right. So, if this holds, then by the implicit function theorem, there is a unique mu equal to mu of x with mu of 0 equal to 0, such that I can write f x comma mu of x equal to 0. Right. So, the reason I am doing this is, now I want to write everything. I do not really want to explicitly compute what is this function mu of x. I want to write everything only in terms of f that is given to me, right, this one. Okay. So, this condition, together with this condition, I will call them, say, star of 1, and say, okay, I can call this 3 and 4, assuming that the first two conditions which we know are f 0 0 is 0, and the partial of f partial of x at 0 0 is also equal to 0. Okay, so what does this mean now in terms of f? So assuming this condition is now satisfied, I can say okay, f x comma mu of x equal to 0 and if I differentiate this with x, so I have df by dx of x mu comma x equal to 0. This actually is the partial of f, the partial of x mu x plus partial of f partial of mu x mu x d mu by dx. Okay. Now I want to find out what is at 0 0. Evaluate this at 0 comma 0, because all these are right at 0, and again this is also at 0. Okay. So I just do some manipulations and I get the following expression: d mu x by d of x at x equal to 0. This is negative partial of f by partial of x at 0 comma 0 divided by df by d mu 0 comma 0. Okay. Now this condition, so what should be true, that the partial of f with partial of x 0 0, the numerator should be 0 and the denominator should not be 0, and this essentially is what ensures that. Similarly, I compute, I will skip some steps here, it should be easy to verify, d2f by dx square at 0 0 so plus df by d mu at 0 0 d2 mu by dx square. So I am just differentiating f. So I start. So this all starts by computing d2f by dx square at x mu of x, and then trying to evaluate this at 0 comma 0. So this will lead to me a condition which looks something like this. This is equal to 0, then d2 mu 0 comma 0 dx square, so this should just be 0. Okay. So what is the condition that should be satisfied, that if I go back, this should actually not be equal to 0, and this is, so d2 mu by dx square at 0 is not equal to 0. This will happen provided d2f by dx square 0 0 is not equal to 0. Okay. To summarize, the conditions for saddle node bifurcation are the following: f at 0 0 is 0, the partial of x equal to at 0 0 is equal to 0. This will ensure the 0 eigenvalue. Okay. And then additional conditions, df by d mu at 0 0 is not equal to 0, this conditions comes via this one, and the last condition would be d2f by dx square 0 comma 0 is not equal to 0. Okay. So, this means this condition. So we are also here interested in relating mu, writing mu as a function of x uniquely, right. So, this should be unique, because in this bifurcation diagram there was only one unique curve passing through the origin, and this why I am assessing on this unique will be clear when I do the transcritical bifurcation. Okay. So, the first condition here ensures that a unique curve of fixed points passes through 0 comma 0, and this ensures that the curve lies only on one side of mu equal to 0. Okay. So, if I were to just write down a Taylor series expansion of a vector field which satisfies these two conditions, it also means that it has a non-hyperbolic fixed point. Fixed point or equilibrium point, which essentially means that it passes through the origin. This Taylor series expansion will look something like this. So, f x comma mu is a 0 mu plus a1 x square plus a2 mu times x plus a3 mu square and some higher order terms. Okay. So, if I just verify these two conditions of df, say I want to verify df by d mu equal to 0, this will give me a condition that a naught should not be equal to 0. I am again verifying that at 0 0. Next would be I am verifying this condition, d2f by dx square is not equal to 0. This will give me a condition that a to a should not be equal to 0, and the second condition would mean that a1 should not be equal to 0. Okay. So, in general I can write a normal form of this bifurcation of the form x dot is mu plus minus x square. We started off saying this x dot is x minus mu square, but I can still do the same when I have x equal to plus mu square, right. Okay, I am so sorry, this actually should be the other way, this should be mu minus x square. Okay, nothing changed, I think this just a typo there. So, I can also write the same say if I just instead say I have a vector field mu plus x square, I would still have, okay, let's quickly do this, right. So, in this case my equilibrium points would be given by x, use a different color for this, x square is minus of mu. Okay. Here for mu greater than 0 there will be no equilibrium, for mu less than 0 I will have two equilibriums, one of which will be stable, one of which would be unstable. So, if I, okay, let me choose another color, so this one. So, this is for mu plus x square. So, I can have that, okay, so on for mu less than greater than 0 I will have no equilibrium is for this vector field, and when mu is less than 0, I will have some equilibrium points here. Okay, you can easily find out which one is the stable one and which one is the unstable one. Okay. This vector field also expresses or also has a saddle node bifurcation, same as this vector field here, right. So the reason why I just said that this should not be equal to 0 is because I started off with a possibility like this, but there could also be a possibility like this, and in both cases this condition is true, d mu by dx at 0 is equal to 0, right. So in general these class of bifurcations can be expressed by vector fields of this form. Okay, so this is essentially called the normal form, and it's kind of easy to do. You can check both of these conditions and draw those bifurcation plots and check why they are actually the same. In both cases you will have a saddle node bifurcation. So in the first case, here if I write it, if my bifurcation plot looks like this, then this quantity here this one, this minus d2f by d x square at 0 0 divided by df by d mu at 0 0 will be greater than 0, and in this kind of bifurcation this will essentially be less than 0. Okay, so this is in general, this is a general normal form of a saddle node bifurcation. Okay, so now that we understand things a little better, we will try to derive quickly the conditions for the other bifurcations. Transcritical bifurcation. Okay, so let us revisit this. In this, okay, two curves of the fixed points, they intersected at the origin, the curves existed on both sides of the line mu equal to 0, and the stability properties changed as they passed through mu equal to 0. Okay, so here we had a unique fixed curve, unique curve of equilibrium points passing through the origin. Here I do not have, the uniqueness is lost here. Here there is no unique fixed curve which passes through x equal to 0 and mu equal to 0 or the origin. That is the first contrast which we see when we compare to the saddle node bifurcation. So when there was a unique fixed point, the requirement was that I should write mu as uniquely as a function of x, and that was possible when df by d mu was not equal to 0. Here there is no unique fixed point, okay, sorry, there is no unique curve that passes through the origin, right. So here we have that two curves of fixed points pass through the origin. Okay. For this to occur, df by d mu should actually be equal to 0. It was supposed to be not equal to 0 for ensuring uniqueness, but here because there is no uniqueness, I would want this guy to actually go to 0. Because if this were not true, there will be only one unique curve that will pass through the origin, but here we have two. So this we should really violate that condition which we were satisfying in the previous case. Okay, so what we know about about the example at hand when we talk of transcritical bifurcation. In that case, we had f x comma mu as mu x minus x square. So, what do I know here is that x equal to 0 is a curve of fixed points or equilibrium points passing through 0 comma 0. This is always true. And therefore, I can rewrite this vector field small f x u as x times some capital F x comma mu. X equal to 0 is always a fixed point. Now, where the f x comma mu is defined in such a way that this is equal to f x comma mu divided by x when x is not equal to 0, and it is defined as df by dx 0 comma mu when x equal to 0. Okay, you can derive this, should be easy. Okay, now x equal to 0 is already a curve of fixed points passing through 0 0, right. Now we want to find additional curve of fixed points that pass through the origin, and therefore we need to now seek conditions not on small f but now on capital F. Where again f has a curve of equilibrium points passing through 0 0. And this f has a curve of zeros or equilibrium points passing through 0 comma 0. So loosely speaking, this f comma 0 0, it will just have a curve like this, right, for f x mu, and this is unique. Okay. Now first thing that we can easily verify is that f of 0 0 is actually equal to 0. Okay. df of capital F by dx at 0 0, this is d2f by dx square is 0 0. So, we will derive conditions on capital F and in turn derive conditions on the small f. That is all we are given, right. We are given the small f. This is d3f by dx square 0 comma 0. And so these three you can verify, right. So, and then we have df by capital F of d mu is d2f by dx d mu at 0 comma 0. Okay. Now for this curve f x mu, right, only this one, I omit this one for the moment. For this we need a unique curve of fixed points passing through the origin, and here x is related to mu. In our example, x was related to mu as x equal to mu, right. So if this is not 0, if df by dx is not equal to 0, then again by the implicit function theorem I can find in a small neighborhood of the origin a function mu of x such that this is equal to 0. Okay. Now in the previous case what we had was that, if I go back to the bifurcation diagram, that the slope should be 0 here, d mu by dx equal to 0. In this case here, for this green for this line x equal to mu, what we want is that the slope should not be 0. It can be whatever, here it's defined by x equal to mu, but in general we would want to ensure a condition that the slope should not be 0. This can be ensured by the following: 0 less than d mu by dx of 0 should not be 0, and at the same time it should also not be infinity. Okay. So, these conditions now we can write in the following way: d mu by dx at 0, this is d to f by d x square 0 comma 0, d to f by dx d mu 0 comma 0. Okay. So, what are now the additional conditions? I need this to be not equal to 0, df by dx not equal to b. So, this will translate to a condition of f in the following way. So, the additional conditions now I need are the following. First is d to f by dx square, this should not be equal to 0. Okay. Now, what we also had was this condition, because for the original vector field there were two curves of equilibrium point passing through the origin. So, this is one, then I have df by d mu at 0 comma 0 is equal to 0. Okay. And lastly, by from this expression here, you can say that d to f by dx d mu 0 0 should also not be equal to 0. Okay. Now, in general, so we said that the slope should not be 0, and in our example we had a curve like this, mu equal to x. Okay. So, in general we could also have a curve which is like this, it could still have the same bifurcation properties, right. So, when we say this, we do not really say that the slope should be positive. So, the magnitude I say, right, d mu by dx should just be bounded and it should not be 0. So, therefore, if I just now look at the normal form, I can write a normal form for this as simply x dot is mu of x plus minus x square. Okay. So, this will give a possibility of these two. The origin, the x equal to 0 will still be the equilibrium point, and then you can possibly have two different sets, right, depending on whether this is mu x minus x square or mu x plus x square. Okay. So, this is my normal form for transcritical bifurcation. Okay. Now, similarly, I will derive the bifurcation conditions for Pitchfork. So, these two conditions plus the standard conditions of the hyperbolic fixed point or the fixed point passing through the origin or a 0 eigenvalue condition. Okay, these are conditions for transcritical bifurcation. Okay, now I will just spend quickly. I'll do the conditions for Pitchfork bifurcation. Okay. So, just as a recap, what happens in this kind of bifurcation is the following, that again you have two curves of fixed points that pass through the origin. Okay. So, in this case two curves of fixed points were passing through the origin. Okay. One was x equal to 0 and the second given by x square is equal to mu. Okay. Now, x equal to 0 existed on both sides of mu equal to 0, and not only that, this x equal to 0 had different stability properties for mu less than 0 where it was stable, and it was unstable for mu greater than 0. Okay. And not only that, after when mu was greater than 0, the other stability, so this guy had the same stability properties, right, for all plus or minus values of x. So, there is a green line all the while. Okay. Now, how do we derive conditions for this? I will quickly give you an idea and write down the final conditions, and the rest should be easy to derive. Okay. So, we will quickly go one by one. So, this should be true all the time. This also should be true all the time. So, additionally here what we see is that is there a unique curve of fixed points that goes through the origin? The answer is no, because you will have two of them as just discussed. So, the third condition should be df by d mu 0 comma 0, this should be equal to 0. So, this will ensure that there is no unique fixed curves, set of fixed curves that pass through the origin. Very similar to what we did in the transcritical bifurcation. Okay. Now, additionally we also require x equal to 0 to be a curve of fixed points. Okay. Which means I should be able to write my vector field as f x dot equal to x some capital F x of mu, where again f of u is defined exactly in a similar way. X equal to 0. Okay. So, in order to have an additional curve apart from x equal to 0 passing through mu x equal to 0, what we must have is f 0 0 equal to 0. Okay. Not only that, now because for this capital F there is a unique curve of fixed points that passes through 0 0, we should have this should be not equal to 0. Okay. There is only one additional set of fixed curves that passes through through 0 0 for this capital F now. Okay. And therefore, I can write now mu the same way as what I did previous. Next, you just try to look at similarities between all the three and the distinctions of all the three cases that we are trying to derive. Okay. And not only that, this mu, right, which is derived for the capital function f, so that unique fixed curve, okay. So, here I am just looking at f x mu x equal to 0, and this mu of x is such that it lies entirely to one side of mu equal to 0. That means d2 mu by dx square is not equal to 0 at 0. Earlier we had derived same condition here, right, d2 mu by dx square should not be equal to 0. This was for small f, not capital F. The small f had a unique set of fixed points for the saddle node bifurcation, whereas here the big F has a unique set of unique equilibrium curve passing through the origin, and it is such that it lies to entirely on one side of it. In the previous case for F, it was lying on both sides in the transcritical bifurcation. So, we are kind of using both conditions that we derived previously. Okay. So, I will just quickly write down the steps now of what these would mean. D mu by dx at 0 is minus df by dx 0 comma 0, df by d mu 0 comma 0 equal to 0. Similarly, d2 mu by dx square. So, I am deriving all conditions now from mu, conditions on mu, so here mu should have been a function of x such that d mu by dx was not equal to 0. I am deriving from mu conditions on capital F and eventually to conditions on small f, as we did in the previous example. At 0, this is negative of d2f by dx square 0 comma 0, this, and then you have df by d mu 0 comma 0, this should not be equal to 0. Okay, and now I know how to write this as functions of small f. This will become, okay, I will just leave this for you to derive, by dx cube by d2f by dx d mu, everything at 0 0, right, and this should not be equal to 0. Okay. So, one additional condition that I can write now here is the following, that from this, if this is not equal to 0, the numerator should not be equal to 0. So, the additional condition is d cube f by df x cube at 0 0 is not equal to 0. Okay. And the next condition, which essentially comes from here, this would look in the following way. Oh, I am so sorry, this was for d mu by dx, sorry, d2 mu by dx square at 0 turns out to be this one, and this guy will turn out to be the following: d mu by dx is minus d2f by dx, sorry, d2 mu, yeah, by dx square over d2f by dx d mu 0 comma 0, this should be 0. For this should be 0, for this to be equal to 0, we need to have two conditions. The first one is that the numerator should be 0, which means d2f by dx square 0 comma 0 should be equal to 0, and the denominator should not be equal to 0. d2f by dx d mu at 0 0, this guy should not be equal to 0. So, this will in general give you conditions to establish pitchfork bifurcation, and I can derive an equivalent normal form now, which looks like this. So, you have x dot is mu x plus minus x cube. Again, you can also derive it from the conditions on the Taylor series expansion. I will just skip those steps of what will be the coefficients a0, a1, a2 and so on. Okay. So, just to recap, so from here, okay. So, what we have done now is just based on observations with some examples and making use of the implicit function theorem and some basic calculus results, derived conditions for a vector field to satisfy, to check whether or not there exist certain kind of bifurcations, transcritical bifurcations, saddle node or pitchfork bifurcations. We will not do the Hopf bifurcation, that is a little more complex because you are looking at 2D bifurcations, but for now we feel it's this much is like enough to give you a general idea on the theory of bifurcations. In the next lecture, so one of our TAs will help you solve with some problems. We will also post some solved problems online, which will help you to solve the assignments. And for more, you can always post questions and we can take up those questions. Thanks for listening.